Welcome to everybody. Again, thanks to the University of Pisa for inviting me to this event. In this presentation, I will discuss briefly the technology about powder bed fusion using laser beam as an energy source, and with a brief introduction to Renishaw as a company, and then discussing a little bit of the of our activity that we've been carrying out in some aspects of the fatigues testing on metallic materials. I'm presenting this as a representative for Renishaw within Italy. However, this presentation is based almost completely on work made by other people. So I don't want to take credit for some work that someone else did. So I specify that this is based on work by these colleagues that are shown in this slide in our offices in the headquarters in the UK. Just a couple of words about Renishaw. We are a global company with headquarters in the UK with about 5,000 employees and offices in 36 countries. We are quoted on the London Stock Exchange, and we started our activities in the 70s with some products that are more related to measurements in the mechanical industry. These is our traditional products, the metrology, industrial metrology systems, and then over time we diversified our activity towards scientific instruments like this spectrometer, healthcare devices, and obviously additive manufacturing, which is the topic of the presentation today. Most of the activity that we do at Renishaw is based on the purpose of our products is improving efficiency, quality of processes for customers. So we make devices and machines and systems that help our customers both in industry and in healthcare to improve their processes and their medical procedures. Regarding additive manufacturing, we started in 2011, purchasing a company that was already building machines that became one of our divisions. When we talk about additive manufacturing at Renishaw, we are involved in metal additive manufacturing. And the technology we use is laser powder bed fusion, which means we have a machine with a process chamber, and powder layers are distributed on the powder bed, and a laser is used as energy source to melt this powder and create solid objects. In the general additive manufacturing ecosystem, our role is the machine manufacturers. So we don't make parts as a third-party provider. We use sometimes additive manufacturing for our production, but our main role is making machines that are then used by companies worldwide to run the additive manufacturing processes. And this is a picture of our manufacturing line in the United Kingdom. If you look at one of our machines, and here I have an animation that shows the general operation of one of our machines for those of you who are not completely familiar with the process. You can identify several functional blocks. The container that is shown here at the top of the machine, if you can see my mouse moving, this container is what we call the powder hopper, the reservoir that stays on the machine containing the raw material, which is the powder, and is filled using bottles like you've seen in the image. At the beginning of the process, when you start, a user starts to build some part, a plate is inserted into the chamber of the machine. You have obviously a software procedure, which includes orientating the part, inserting supports and slicing the part in several layers, very thin layers, as we'll see a bit further on. Then the operating file is loaded onto the machine and the process is started. The first thing that the machine will do is to remove the oxygen from the process chamber, and that is something we specifically do. It's one of our patents, to clean the atmosphere within the process chamber in the best possible way, and we insert the inert gas. All additive manufacturing machines that use laser as a powder source use some form of inert gas. What is specific to our machines is the fact that we create a vacuum inside the machine before inserting the inert gas. Then the machine will start spreading powder and melting with the laser. The powder that comes from the hopper that is here at the back of the machine is deployed on the powder bed and then spread with this part that we call the recoater. Any additional powder that we spread will, to ensure that we cover properly the powder bed, will end up in the powder recovery slot at the front of the machine. During the operation, we have a platform that is effectively the z-axis of the machine that moves downwards, giving the part its vertical height and dimension. All the powder that is used during this process can be recycled. The powder that is not melted into a solid piece, naturally, and it will end up in one of these containers that are then taken to a separate sieving device that will clean the powder by sieving it. What we're showing here is the operation of one of the more manual machines that includes a separate sieving outside of the machine. Some of our machines also include internal sieving included in the main device. So this operation is not needed anymore, and those machines are meant more for a production environment rather than for a research and development environment. As the process continues, deploying other layers of powders, we also have a very important part of the process, which is the gas flow that is continuously cleaning the process chamber from sparks and emissions coming from the process. This is essential to make sure that the laser power is deployed and reaches the powder bed in the correct way. This gas flow that contains metallic particulate is then filtered through a paper filter and recirculated in the machine. So the process continues, and this way each layer is added to the height of the part and will end up in a final metallic device. At the end of the process, the operator, using a glove compartment, cleans out the remaining powder from the machine, sending it to the sieving process, and extracts the plate with the part welded on it. Additive manufacturing for metal is a technology that is not replacing other technologies. It's something that is incremental and will help in a specific way. So creating things that could not be made before in an easy way. The key benefits are the ability to produce complex geometries, make in one single part what needed in the past to be made with different separate parts and then assembled, create items and parts that have a considerable reduction in weight, a specific benefit that is very important, for example, for aerospace applications, and the possibility to create components that are fully customized, very important, for example, for medical application or for high-end consumer goods customizations. In addition to this, parts can be manufactured directly without tooling, so that cuts in the overall time of the manufacturing process and in the costs of it. And it also enables rapid design iteration, so you can change design very quickly and immediately print another part. Now, we're coming to the topic of today's seminar, which is the importance of fatigue in AM materials. In more and more applications that use AM materials as a critical part, we have many benefits because of the lightweight parts we can build, and of course because of the performance of the materials that are normally higher than the traditional materials. However, in some cases, of course, the process can generate defects in the parts, and these will affect very strongly the fatigue performance. So it's really important to identify these possible defects that can come out as an outcome of the process, as an unwanted outcome of the process. In general terms, laser powder bed fusion produces very thin metallic microstructure. The image you see on the right hand side, the larger features that you see are the melt tracks and the melt pools, and the finer features that you see are the boundaries and grains of cells that you can see sometimes are aligned in certain specific directions. So this is a positive feature of the technology that improves in general the mechanical properties. It will also pose some interesting challenges about thermal treatments and the performance of the materials in the long term. Again, in general, sorry, one slide too many. We have small melt pools, and the microstructure and alignment of the metallic grains is very fine, specifically in the horizontal plane, while on the vertical plane, due to melting and remelting, sometimes we have elongation of the grain. Anyway, we're talking about grains in the region of 20-30 micron in the XY plane. Looking at the defects that can arise from additive manufacturing process, certainly an important point is about the chemistry. The alloys that we use are very well controlled in terms of oxygen and nitrogen content, and the reason for that is that, as you know, these interstitial elements can insert themselves inside the intermetallic matrix to generate distortions and modify the ductility and the performance of the material. In general terms, the insertion of interstitial elements will increase the total tensile strength of the material and the hardness, and will reduce the elongation, so it will reduce the ductility of the material. So if we look at the way that oxygen can get into the alloy, there's basically two ways, oxygen and nitrogen. These two ways are if the atoms of oxygen and nitrogen are already included in the alloy itself, or if they're taken into the alloy by the process. We want to achieve alloys with very low content of oxygen and nitrogen to achieve the best possible elongation and resistance to fatigue. However, the environment around us is not helping us, so we want to control the inert behavior of the machine, the inert atmosphere of the machine, to a very tight specification. In here, you can see what happens. See if I can share my mouse. Go back one slide. Okay. This behavior, this red line, is a machine that is not behaving properly, so it continues to leak argon, and you have to purge the machine regularly, and you still have a concentration of oxygen that is unwanted inside the inner chamber. This behavior is a good machine that once you have an initial purge phase, and then maybe in the first 100 layers absorption of oxygen by the metallic parts that are melting over the plate, will keep a low oxygen content throughout the build. This is what we're aiming and what our machines are designed to do. Another type of defect is related to emissions from the melt pool that can create defects like this one. You see here you have about 50 micron dimensions, so this defect is about 150 micron across. This is, if you think about the process, and this is the horizontal plane, this defect is generated by a spatter part that is in this area that has covered the plate, and it has generated a cavity underneath and did not allow the laser energy to reach properly the powder. That is then left unmelted. So you have all sorts of different defects that arise from the process if it's not adjusted properly. Most of these defects will be cured by a good gas flow. Here you see a simulation, the result of a simulation of the gas flow that moves argon gas vertically in the chamber and then horizontally to remove it from the chamber. Main production machine is a machine with 4 lasers. Here you can see a video of the 4 lasers operating at the same time on a single part. This machine will greatly improve the productivity. However, it also poses a lot of challenges to achieve a good gas flow that removes all the particulate from the chamber. If you look at a good part that is coming out of this process, these are micrographies. You can find the densities that exceed 99.99%. Sometimes you have very small porosity, like in this area. However, the bulk of the part is very dense. So this is the first step when you develop a material to achieve very good density. A second step is to achieve good tensile properties, consistent all over the powder bed and consistent in time and over different processes. And then you achieve the fatigue properties. If you look at tensile properties, you have a comparison. This is the comparison between a standard material, in this case is titanium alloy grade 5, from the handbook used in the aerospace industry for materials, and the material you obtain with our process during laser powder bed melting. If you look at fatigue performance, this is some results we are obtaining, but I will not discuss fatigue results very widely, because many presentations after mine will discuss this in more detail. However, we have some hopefully good results for the future of the technology, because the typical curve for traditional materials is overridden by the curve for our material generated with our process. So we achieve very high cycles fatigue and very high stresses before breaking. One aspect that is extremely important for the fatigue in AM processes is the surface finish, as in any process, but specifically because AM will not return parts that have a very high polish surface. Normally, the parts that come out of AM process have rough surfaces and parts and powder beads attached to the surface. This will generate a lot of micro notches on the surface that can lead to defects. So there is a big difference between parts that have been tested as built or after machining. As in some cases, parts need to be used as built, this is definitely a field of research to achieve the best possible surface quality to improve the fatigue resistance. So I'm slightly exceeding my time, but I'm just summarizing that laser powder bed fusion actually is a process that has, as a result, a unique, fantastic thin microstructure. It can provide very high performance in terms of tensile strength and elongation if it's done properly. And there is a lot of work to do on fatigue, which is good news for the research in the university, because that will affect a lot the possibility to apply additive manufacturing to a lot of processes in the future, especially in the aerospace and automotive industry. So thanks for leaving me this space, and I will return the microphone to the university.